Michael Wolf from the PGI Compiler Group. Today we're going to be talking about OpenACC, asynchronous data transfers, the use of pinned memory, and the advantages and disadvantages thereof. What I have here is a completely artificial application. What I have at the bottom of the loop, there's a timing loop, this iter loop. Inside here, there's a J loop that goes through the rows of the array, and it calls a routine. This routine has a parallel loop, which some artificial computation is to take up some time, and then updates the host for that row of the array. I'm going to build this and run this on the machine I have here today. The accelerator I'm running on, using the PGI PGXL info tool, tells me I'm running on a Tesla K40, compute capability 3.5. So I'll build my application targeting compute capability 3.5, and I'm going to time this with 100 iterations of that timing loop. This is going to take about exactly 4.27 seconds. I'm going to take a slightly modified version of the same application using asynchronous data transfers. The only difference between this version and the previous version is the async clause on the parallel loop and the associated update construct. The queue number, the queue argument, is the queue to use. It's a number between 0 and 16. It will tell me which asynchronous queue, or if you're a CUDA programmer, which CUDA stream to use. I'll build this with the same compiler. I'm using the latest 17.1 compilers, which are brand new as of today. With the same argument, 100 iterations, you'll find it runs in under 3 seconds. So it's a more than 25% performance improvement. What accounts for that? Let's take a look at the profiler, at what we can see with the how the program executes on the device. So I'll first start with the synchronous version, and I'm only going to run it for 5 iterations because that's all we need to get the characteristics we want. Profiler is running and collecting the data information. And I'm going to zoom into the steady state down here. And what we're going to see is the body of the loop. It does the compute and then the data transfer. Compute and data transfer. Compute and data transfer. There's no overlap between the compute and the data transfer. There's a little bit of dead space between there too. We'll come back to that. Let's take a look now at if I run the asynchronous version. Again with 5 iterations. I'm disabling the unified memory profiling because the system I have now does not support unified memory profiling. And here we are. Again, I'm going to zoom in on the steady state. We see the data transfers and compute are backed up one right against each other. There's no pauses between the transfer and the compute, so the GPU is busy doing one thing or the other all the time. In fact, if we scroll a little lower, we see all the data transfers are happening on different queues. So what's happening on the host at this time? Well, let's dive in right here. What we see if we dive in right here, and if I hover over these little boxes in the driver API, here it's launching a routine and launching the data movement. And then launching a routine and launching data movement. So the host actually is doing all its computation for all the rows all at once. And then I scroll over a little bit, and here, this is where the host is now waiting. So the host is no longer busy, it's just waiting on the GPU. And you see now I'm doing computation and data transfer simultaneously because they're being executed on different queues or different CUDA streams. And when one computation is winding down, the next one already starts. So there's a little bit of overlap in computation as well. So that's the reason for the improvement in performance between the synchronous and the asynchronous versions. Let's scroll a little bit farther to the right. What's going on here? There's not a lot going on. So this is about 4 milliseconds when there's nothing happening. What is happening here? Well, this has to do with how data transfers happen between the host and the GPU. Okay, so here we have our system. I have my multi-core CPU over here on the left with its system memory, very large system memory. I have the GPU here on the right and its own device memory. The link between them today is a PCI Express. In the future, with IBM Power Systems, this could be an NVLink. I have my array over on the system memory, and I have a device copy of that array managed by OpenACC. What I want to do is to take the data from this array and update the appropriate row in the host memory. And the way that's done is there's a little DMA engine, direct memory access engine, in the GPU that will do this asynchronously from both computation on the host and on the device, which is how this works. But the DMA engine isn't very smart. It doesn't know what virtual memory is. The problem is this memory here, this array is set in system virtual memory. It's paged. It might not all be contiguous. You might have a page here and a page over there and a page someplace else. And some of those pages, well, the operating system can page them back out to disk. What's the DMA engine going to do? Well, it can't do much of anything. So the way this works is either the OpenACC runtime or the CUDA driver is going to allocate a pinned buffer. A pinned buffer is a block of contiguous physical memory in the system memory space. And then the DMA engine will be given the address of that pinned buffer as its target. So all the data will be copied into this pinned buffer. After that transfer is done, then the CPU will copy the data back from the pinned buffer into the user space. And that's the gap that we're seeing at the end when the CPU was waiting for all the transfers to be done, was the driver or the OpenACC runtime doing these copy backs. Is there a way to attack that? Well, that's why we're going to use the pinned option momentarily. Okay, we're back at the screen here. I'm going to pause this PG-prof and build a version of the same program, the asynchronous program, with pinned memory. So the only difference between this build and the last build was on the t=Tesla command, I added the pinned option. What the pinned option will do is take all dynamic memory allocations that would be malloc, calloc, and free for C, your new and delete in C++, you allocate and deallocate in Fortran, and turn them into versions that are using pinned memory. They allocate the data in pinned memory. It has to be specified on both the compile line and the link line when you're doing separate compilation. Now if I run this program with the same iteration count, we'll see that it runs, somewhat faster. I picked up another 0.6 seconds. Well, let's look at the profiler again and profile that example. I'm going to start another profile run using the pinned executable, again with 5 iterations. And while it's generating that timeline, what we're going to see is that gap at the end when the CPU is waiting for that block of GPU executions and data transfers to happen. There'll be no gap whatsoever. The gap should disappear. And here we are. I'm going to dive into where we're down to our steady state. And I'm doing compute, 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 compute. There's a little overlap between the compute steps and doing data transfers back to the host. And this is where the CPU was waiting for the GPU to finish, and then it starts the next iteration. And the CPU does all of its enqueuing operations immediately and keeps the GPU busy, so the data transfers and the compute, the GPU is basically busy all the time. Now, that's the advantage. The disadvantages. Let's look at this a little bit more carefully. The disadvantage is that we have to use pinned memory allocations to allocate this dynamic memory. And pinned memory allocations are expensive. They're expensive because they're expensive at the operating system level. The operating system has to find a block of contiguous memory and make sure it won't get paged. The deallocate is also expensive because the CUDA driver has to make sure there are no pending data transfers going to go to that pinned memory. So it has to wait until the GPU is idle before it can deallocate pinned memory. So the advantages are your data transfers are faster, they don't incur the extra data movement from the pin buffer back to user space, and if you're using asynchronous transfers, you get more asynchronous operation between the host and the GPU. The disadvantages are the extra cost of the allocate and deallocate, and if you have huge data buffers, huge arrays, you actually can run out of pinned memory. And it's not necessarily the case that it'll run out the same place all the time. It may run out depending on what else is running on your machine at the time. So that's a summary of asynchronous data transfers and using pinned memory to optimize them. They're available with the PGI compilers with OpenACC, I hope you're able to use this information in your programs. Thanks for your time.